Hello everybody. Today we're going to talk about section 2.3, limit techniques. So, just as a review, yesterday, or in the video that hopefully you watched yesterday, we talked about the idea of a limit. Not evaluation, just what happens nearby. Okay? And so we do something like the limit as x approaches 3 of 2x plus 1 over x minus 3. Note, we cannot directly plug x equals 3 into this. Doesn't work when x equals 3 because we're going to divide by 0. So the answer becomes, what can we do? Well, sometimes we can take a limit. And so the idea is, how can we directly prove? So we talked about tables yesterday in the previous video. We talked about graphs, and those are good, but really the big thing is we want to go algebraic. That's really what we want. We want this system of steps in the same way that you can do 3x plus 4 equals 10. There's these algebraic steps that we all agree about that brings the answer to be 2. I don't have to make any arguments that the answer is 2. I just seem to be able to directly show it. So the question is, what are some techniques that we can do to create these limits? So first, I want to talk about some rules for limits, and these are going to be really, really important as you go, especially from this class to something like Calculus 2. You start to really talk about what does it mean for these limits to converge? What does it mean for these limits to exist? And so just so you know, just to make these things work, f of x is a function with a limit. And I'm also going to say that c is a constant number. Okay? So, what are a couple rules that we can talk about our limit? So, the limit as x approaches a of a constant times the function. The constant can be pulled out of the limit as long as the constant doesn't depend on x, and constants never depend on x. We actually pull out that constant, and we can say it's c times the limit as x approaches a of f of x. So, anytime you have constants, we can pull these apart. For example, what is the limit as x approaches 9 of 3x plus 4 squared? We can pull out this 3 and say this is 3 times the limit as x approaches 9 of the term x plus 4 squared. Okay? That's one thing that we can do. Now, we would never really do it in this case, but the whole idea is that we can take out these limits. Now, here is the most important thing. Or here's another very important thing. Another thing that we can do with limits is the limit as x approaches a of some division. Let's say x times f of x divided by g times g of x. So we have these constant x terms out. And the idea is we can actually cancel the effect that those two things have. We can cancel through division. And this might seem real normal. However, I will point out this actually allows us to do one thing that we couldn't do before. So the question is, what is 0 divided by 0? Answer, I don't know. I don't know. And it's me being completely honest with you. There's lots of good answers. But I can tell you one thing with limits. The limit as x approaches 0 of x divided by x is the limit as x approaches 0 of 1 is 1. This canceling only exists in this limit environment, and I want to really specify it. The limit environment allows x divided by x to act like, and I don't even really want to write equals, I want to say x divided by x to act like 1. Even though x divided by x in general does not equal 1. Why? Well, it's because 0 divided by 0 does not equal 1. Okay? Now, those are the big ones right now. There are a couple more. Limits also behave kind of well. And maybe this is a time for me to maybe bring something up like a textbook. In case you're wondering. There is maybe a better list that I'll show. So just real quick, these are sometimes referred to as the limit laws. Assume that limit as x approaches a and limit as x approaches a of g, f and g both exist. C is a constant number and n is some larger than 0 integer. So one thing is that the sum of limits is the limit of the sums. The limit of the difference is the difference of the limits. There's this distributive property that limits have. We actually call it being a linear operator, which we'll talk about later. Products, all good. Quotient, this is really important. You can split a limit into its quotient, provided that one of them is not 0. Okay, specifically the denominator. If the limit of g of x is 0, as x approaches a, then this breaks down because we still have that dividing by 0 rule. Okay? So, I just wanted us to be made aware of those things. Again, those are the limit laws. If you ever want to just look up the limit, and I'll write this down, the limit laws. And again, they behave pretty much identically. We're going to focus on a really specific set of examples, and I'm going to break these into 3 examples. So there's factoring, there's like denominators, and there's also going to be radicals. Okay, I'm going to do one example of each of these, and hopefully that's the template that you can use when you need to find these things. So we're going to start off with our first one. What does a factoring type look like? We're going to replace polynomials with their factors. So, as an example, you can write something like x squared plus 2x plus 1. You actually write that as the multiplication of these two factors, x plus 1 times x plus 1. If you allow me to kind of distribute these things apart, there's x squared plus x plus x. First outer, inner, last, plus 1. Notice altogether, we get x squared plus 2x plus 1. So the question is, how do we go from this expression to this expression? So you're going to do a lot of these, but here's one way to kind of think about it. If we think about it, we need to multiply 2b x squared. We also need to multiply 2b6, but slightly differently. We actually need to add to be 5 is really what we're trying to think of. So let's get some base case out of the way, and hopefully this is something you talked about in your pre-calculus classes. So I'm going to say there's going to be an x and an x. Notice x times x, that multiplies to be x squared. We're good. Now, what's going to multiply to equal 6? So 6, I have 1 times 6. I also have 2 times 3. So I could write plus 1 plus 6. Notice the 1 times the 6 does give me 6. But my question is, if I look at the outer inners, 6x plus x would actually give me 7x. And that's not what I want. So unfortunately, that does not work. And most of these are going to be simple enough that hopefully you'll be able to find them. So when the 1 minus 6 doesn't work, I hope that your inclination is, let's try x plus 2 and x plus 3. And that actually does work out. Again, x times x, x squared. 2 times 3, 6. 3x plus 2x is 5. We're good there. So how does this help us with factoring? Well, let's take a look at, this is a direct one from your homework. This is the limit as x approaches negative 1 of the fraction 2x minus 3 squared minus 25 divided by x plus 1. So notice, not something that I can plug in negative 1. I'm going to get 0 bad on the denominator. Okay, so we need to use some limits. So the first thing that I'm going to do, notice I'm keeping the limit. I haven't actually evaluated that. First thing I'm going to do is I'm going to expand this term right here, because I really just want just a polynomial in my numerator. So what is 2x minus 3 squared? Well, that's 2x minus 3 times 2x minus 3. Once again, doing that expansion out, that gives me 4x squared minus 6x minus 6x plus 9. Altogether, 4x squared minus 12x plus 9. Don't forget, we're going to subtract 25 from that, and we're going to divide it by x plus 1. So, sorry about the different colors. Okay. First thing I want to do, though, before I go on, I can combine the plus 9 and the minus 25. I think that'll give me minus 16. Whoops. It's a good idea to check yourself on a calculator. Yeah, okay, I think we're good. All right, we're going to keep going. Now, I can rewrite this factoring, this 4x squared minus 12x minus 16. So I'm going to use my first rule. I'm actually going to divide out, notice each of these terms, I can divide out a 4. And I can divide that 4 all the way out, remember our first rule, to the very beginning of the limit. This is actually going to be 4 times, I'm just going to use a dot for multiplication, the limit as x approaches negative 1. 4x squared divided by 4 is x squared, 12 divided by 4 is 3x, and 16 divided by 4 is 4, all divided by x plus 1. Okay? So, what have I been able to do? I've been able to turn the original limit using our properties. I just expanded it out. I just divided out the 4. I managed to get this limit. So really, what I want to focus on is I want to focus on what this limit is. So, I'm going to try this. I'm really trying to, I messed that up greatly. I'm really trying to utilize some of these features. I don't know why that keeps happening. One more time. Would you look at that? Just learned a new trick. Okay, we're going to keep going based on this. Okay, so this is the limit as x approaches negative 1 of the term x squared minus 3x minus 4. And I want to focus in on this x squared minus 3x minus 4. I want to try and rewrite that factored form. So first of all, what's going to multiply to be x squared? That's going to be x times x. Now, what multiplies to equal negative 4? So notice, I actually have even more options than we thought previously. I have negative 2 times positive 2, negative 1 times positive 4, but I also have 1 times negative 4. Technically, I could also make this one up. And so my question is, each of these will multiply to equal negative 4, and they'll go here. But which of these are going to combine to equal negative 3? So if I add those together, I get 0. If I add those together, I get positive 3. And if I add those together, I get negative 3. That's the one that I want. So I'll do x plus 1 and x minus 4. And you can check, multiplying this out, you do get that back together. So this is the limit as x approaches negative 1 of the term x plus 1 times x minus 4 divided by x plus 1. And that rule, normally you can't do this, but because, and let me emphasize this, because I am talking about the limit, x does not equal negative 1, therefore x plus 1 does not equal 0, I am not dividing by 0. So I can cancel the x plus 1 in the numerator and the x plus 1 in the denominator. So notice what I'm going to get is the limit as x approaches negative 1 of just x minus 4, which turns out to be, now I can directly plug in. And I want to stop real quick right here, and I just want to give you guys a shout out on your homework. Lots of homework questions want this. They want this form of your question. And to bring back in the multiply by 4 that I kind of omitted, lots of homework questions are going to want this as the answer. In that, they like you to show steps. So don't just try to get to the right answer. Also try to work on the algebraic side of things and make sure that we're getting it. But now we can directly plug in, and this is going to be 4 times negative 1 minus 4, which turns out to be 4 times negative 1 minus 4. It's going to be negative 5. And the answer we get is negative 20. Which turns out to be the right answer. So that's an example of our factoring type limit, where we're going to replace a polynomial with factors. On to our second type. This was like denominators. Okay, and this happens a lot. So let's take the limit. We're going to switch up our variables. It's very common to see h represents change, and we'll talk more about that when we get to our instantaneous rate of change questions. But let's take a look at something like this. The limit as h approaches 0 of, this is going to be a double fraction, 8 divided by 9 plus h minus 8 divided by 9 all divided by h. Okay? So the fundamental question that we need to answer is, how do we combine the numerator? Okay? And so we're going to use something that hopefully you guys have seen, which is the concept of like denominators. So let's say I wanted to add 1/2 and 1/3. Notice I can multiply the first term by 3 over 3 and get 3/6. I can multiply the second term by 2 over 2. Reminder, I'm just multiplying by 2. Or sorry, multiplying by 1. I can get 2/6. And once you have the like denominator, the 6 on the bottom equals the 6 on the bottom, we can directly add the top, and we can combine our fractions as 2 plus 3 equaling 5. We want to do the same thing here, but the question is, what is our like denominator? So on the one hand, we have 8 over 9 plus h. But on the other hand, we have 8 over 9. So what are we going to multiply? Remember, we multiply each of these by some form of 1. So we're going to multiply this one by 9 plus h divided by 9 plus h. And we're going to multiply the first one by the other denominator. We're going to multiply it by 9 over 9. Okay, we'll start off with the slightly easier one. 8 times 9, I think that's 72. Over, distributing out this 9, I think it's going to be 81 plus 9h. Don't forget our subtraction. And now what will we get for the right-hand one? So once again, 8 times 9, that should be 72 plus 8h, all divided by 9 times 9 and 9 times h, 81 plus 9h. These two things are the same, which means we can combine them. And actually, I think that went a little high. We can combine them as 72 minus 72 minus 8h. Don't forget this negative sign. We're subtracting the whole thing. All divided by 81 plus 9h. The 72's cancel. This is negative 8h divided by 81 plus 9h. That's what we can replace the numerator in this original limit with. So the limit is h approaches 0 of 8 divided by 9 plus h minus the term 8 divided by 9 all over an h can be rewritten as the limit as h approaches 0 of negative 8h divided by 81 plus 9h divided by an additional h. And I really try to emphasize that this fraction symbol is smaller than this fraction symbol. It's this fraction divided by this fraction. Now, one of the things that you can do is you can always rewrite this. So this is something like a divided by b divided by c divided by d is a times d divided by b times c. That's just one of our fraction rules. So expanding this out, the limit is h approaches 0 of, this is negative 8h divided by h times 81 plus 9h. And wouldn't you know it, bracket, we have an h in the bottom and an h in the top. H divided by h does not equal 1. But because we are in a limit environment, h does not equal 0, we can divide this h and this h, which allows us to write the limit as h approaches 0 of negative 8 over 81 plus 9h. And at this point, we are ready to plug in. And we're just going to directly plug in, and we're going to get negative 8 over 81. And that is the answer to our limit. So how are we able to do this? We just have to make like denominators, and we create a situation where we get a cancellation. And that's really the point. In limits, you're always working to deal with some type of cancellation. You're always going to want something to be simpler than it was previously. So we've talked about factoring, we've talked about like denominators. This one is the slightly harder one, called dealing with radicals. Okay? So you're going to look at some limits that contain things like square roots. We call this symbol, we call this a radical symbol. Okay? So how do we deal with that? Well, let's take a look at the limit. Once again, as h approaches 0, we're going to take a lot of limits as h approaches 0, of the fraction, the square root of 9 plus h minus 3 divided by h. So if we could bring this h out, it would be all hunky-dory and we could cancel, but unfortunately the h is trapped in a radical. So how do we do that? Well, we're going to use a property that's sometimes called rationalizing a radical. Okay, so there are two ways to do this. Number one is to square it. But unfortunately, that's not going to help us. But there's a really weird trick that if you take the square root of, just arbitrarily, x plus c, and you multiply it by the square root of x, well, sorry, not the square root of x plus c. Let me erase that. So this is the square root of x plus c. We're going to multiply that by the square root of x minus c. The square root of x times the square root of x, we get x. We get negative c the square root of x plus c the square root of x, gone, minus c squared. And that's what we want to do. We want to introduce what is sometimes called the, it's not necessarily an inverse, but it's sometimes referred to as a conjugate, where we go from a plus b, a minus bi. Those are conjugates. This is using that, of course, the imaginary element. There's radical. There's a plus the square root of b, a minus the square root of b. Those are also conjugates. So the question is, what is the conjugate? Well, if we call this thing a and this thing b, I'm going to rewrite this limit as h approaches 0 of, making myself a little bit wider, it's going to be the square root of 9 plus h minus 3 times, if that's a minus b, I want to do the a plus b. So a plus b, but in order to keep this equal to 1, I'm going to multiply both top and bottom. And so let me get rid of that real quick. So we originally had an h, but we're going to multiply that h by an additional, the square root of 9 plus h plus 3. Okay, let's keep this limit going. This is going to be the limit as h approaches 0 of, so once again, factoring, the square root times the square root. This is just going to knock out that 9 plus h. We're going to pick up plus 3 the square root of 9 plus h. But remember, this is why we did the conjugate. When we do a negative, we're going to subtract 3 the square root of 9 plus h. And that term and that term are going to cancel. Don't forget, we do have a minus 9, which means that term cancels and that term cancels, leaving us just with h. Now on bottom, we have h divided by the square root of 9 plus h plus 3. We don't typically like to expand things unless we know for sure they're going to cancel. Okay? Now, giving myself just a little bit more room, I'm going to erase these conjugates. Notice, once again, we've created a system where we have an h divided by an h. And if you really think about it, the only thing we have left on the numerator is h, and we have an h left in the denominator. Gone, gone, gone. All these things canceled. And again, h divided by h is not equal to 1. I'm not saying that. I'm not saying that h divided by h is equal to 1. I'm saying that in a limit environment, I can cancel those h's. So we get 1 divided by the square root of 9 plus h plus 3. Notice, this is something that we can now plug in. And so this is going to be 1 over the square root of 9 plus 3, which I think is 1 over 3 plus 3, which is 1 over 6. So, just to make sure we're all on the same page, when it comes to our techniques, we really have three main techniques that we're going to target. We might need to do some factoring. We might need to create like denominators, and we might have to deal with radicals. And what are the methods here? Well, unfortunately for factoring, that's just what we have to do. There are some advanced techniques like the quadratic formula, but by and large, that's not something that I think you're going to need. Like denominators, again, we're going to multiply by the other denominator, specifically top and bottom. And for radicals, we're going to multiply by the conjugate. Remember, we just turned positive, interesting parts into negative parts. I hope you are having a wonderful start of the class, and if you have any questions, please let me know. Take care.